modeling exponential behavior, and we are going to use exponential functions to model real-life situations. Here's a graph of a function f defined by f of x equals 400 times 0.2 to the x power. Number 1 is identify the approximate graphing window shown. So work that out right now. And your graphing window would be 0 is less than x is less than 44, and 0 is less than y is less than 1100, or equivalent. Number 2, suggest a new graphing window that would A, make the graph more informative and meaningful, and B, make the graph less informative and meaningful. So for A, one example would be 0 is less than x is less than 10, and 0 is less than y is less than 450. The window would include x values where meaningful changes happen and exclude the parts where the changes are very small. The y values are limited to values that matter between 0 and 400, allowing us to see more clearly the changes in that range. And then B, negative 10 is less than x is less than 80, and 10 is less than y is less than 100. This window would show a lot of useless x values and cut off the y values at 100, which would hide the behavior of the function when x is between 0 and 1. Height of a tennis ball after bouncing several times on a concrete surface. So use the table on the right side to help you work through this problem. Number 1, which is more appropriate for modeling the maximum height h in centimeters of the tennis ball after n bounces? A linear function or an exponential function? So here we would want to graph it out and see what it looks like. And so a rough graph of this would look like this. So it would be exponential because the lines aren't in a straight line. Number 2, regulations say that a tennis ball dropped on concrete should rebound to a height between 53% and 58% of the height from which it is dropped. Does the tennis ball here meet this requirement? So you could say yes, because the first rebound is a little over 53%, and the second is almost 54%, and the fourth is 55%. The third rebound is only about 47%, but there could be some measurement error. Or you could say no, because the third rebound is less than 50% of the height from which the tennis ball fell, falling out of the allowable range. And then number 3, write an equation that models the bounce height h after n bounces for this tennis ball. So here's the equation. H equals 150 times 0.53 to the n power. And then a factor of exactly 0.5 would also work. And then number 4, about how many bounces will it take before the rebound height of the tennis ball is less than 1 centimeter? And explain your reasoning. So here we would find it to be about 8 bounces, because the height of the ball is decreasing by a factor of about half after each bounce. So after 3 more bounces, it will decrease by a factor of about 1/8, giving a little more than 1 centimeter, but after 4 more bounces, it will decrease by a factor of about 1/16. You are supposed to fill out your own table, but I'm giving you these numbers since we won't be doing all the testing that goes with it. And so in your table, you can fill out the numbers that are right here. And these are not the right measurements for each ball, but I just labeled it so you can see the difference that would happen. So number 2, which one appears to be the bounciest and which one appears to be the least bouncy? So the second ball is the bounciest. The balls were dropped from the same height and its bounces are the highest. And then the third ball is the least bouncy. Number 3, for each one, write an equation expressing the bounce height in terms of the bounce number n. So ball 1, it would be 150 times half to the n power, or it would be 150 times 0.5 to the n power. Either way you want to write it is fine. Ball 2, you would have 150 times 7 over 10 to the n power, or you can do 0.7 in place of 7/10. And then ball 3, you would have 150 times 2/5 to the n power. Number 4, explain how the equations could tell us which one is the most bouncy. The bounciness of the ball is measured by the rebound factor, which is the base of the exponential expression, that is half for the first ball, 7/10 for the second ball, and 2/5 for the third ball. The larger this number, the bouncier the ball. And then number 5, if the bounciest one were dropped from a height of 300 centimeters, what equation would model its bounce height h? And so we would write h equals 300 times 7 over 10 to the n power. Ball after a certain number of bounces. So looking at this table, is this ball more or less bouncy than the tennis ball in the earlier task? So this ball is more bouncy. Each bounce of this ball reaches a height that is about 0.7 times that of the previous bounce. The tennis ball in the earlier task loses about half of its height with each bounce. From what height was the ball dropped? Explain or show your reasoning. So it was dropped at about 150 centimeters, and how you would find that, you would do 73.5 divided by 0.7 equals 105, and 105 divided by 0.7 is 150. Write an equation that represents the bounce height of the ball h in centimeters after n bounces. So one way we could write that is h equals 150 times 0.7 to the n power. And then number 4, which graph would more appropriately represent the equation for h? Graph A or graph B, and explain why. So graph B is more appropriate. Only whole number n values make sense in this context. We cannot have bounce number 3.4. And then 5, will the nth bounce of this ball be lower than the nth bounce of the tennis ball? Explain your reasoning. And the answer is no. The height of this ball after any given bounce will not be lower than that of the tennis ball because they were dropped from the same height, and this ball has a greater rebound factor, so it will always bounce up to a higher point than the tennis ball.